So we're going to talk about enthalpy. Maybe. Enthalpy. Oh, that's right. Okay. So these are terms we talked about before. Endo meaning in. So if something's endothermic, means that energy is going in. Endothermic, energy in. Okay, so endothermic process is one that requires energy. We could also say that energy is needed, energy is added, energy absorbed, energy, it takes energy, all of those things. But remember what we've been talking about, a system. And tomorrow, your system, actually the next 2 labs, your system's going to be a coffee cup. But so that's endothermic, energy in. And we actually also have been talking about Q is equal to MC sub P delta T. Q is the change in thermal energy. Remember? And we said that the sign of Q, whether it's positive or negative, has its consequences. We said that if it's positive, that's all consistent with that increasing its temperature. So remember, delta T is, T sub F minus T sub I. So the final temperature is greater than the initial temperature. So hopefully this is all kind of ringing a bell. So Q is positive for endothermic reactions, right? So this might be an I said endothermic reactions. I shouldn't have. This is endothermic processes, which could be a reaction, but this is just a phase change. All we're doing is taking an ice cube and melting it. How would you melt an ice cube? You heat it up. What does heating it up mean? It means adding thermal energy. So melting an ice cube is an endothermic process. Okay, and we talked about the system and the boundary, and then outside the system's boundary is the surroundings, right? And then the surroundings plus the system is equal to actually what we call the universe. So that's what that kind of looks like. And I didn't bring these. Let's go back up. Did I do hot packs for you guys before? No. You should have a Well, actually, these will be for a few slides from now. So this is a prop for. But I don't know if you've ever been to the ER and they're like, "Oh, dude, your knee is so swollen. We better get some ice on that." And if they don't have ice, they have a freezer. You can actually have with you a little, like this shows up here, a little pack that once you let the reactants mix, like that reactants are isolated. Once the reactants mix, it becomes cold. So you might be, well, how comes that's endothermic? Well, here you go. Basically, the reason it gets cold on your knee is because it is sucking all of, not the air, it is sucking all the thermal energy out of the region around it. It's endothermic. Okay, so it's endothermic. It gets cold. It's endothermic.
That's why it makes your knee cold, because it's taking the heat from your knee.
It's taking the heat from your knee. And if you just have it on the table and kind of have a radar gun, that little gun thing, the infrared gun, you can actually see the air around it getting cold. Because it's, but for your knee, it's taking the thermal energy from your knee.
It's pretty cool.
Yeah. So the world is just constantly
Exchanging energies.
Yeah.
Or creating.
Yeah. If something gets cold like that, yeah. Don't worry too much about it. Okay, so endothermic is heat in, okay? And in the case of the cold pack in your knee is kind of like the surroundings, okay? And the system is the cold pack. So exothermic then is a situation in which a system will release energy during a process, a chemical reaction, a phase change, okay? So when we say it releases energy, we could use liberates, evolves, produces. And if I was going to show it, I know this, I don't mean to confuse you, but, well, I'll do another one. Ugliest thing. Okay, so this is my system, and so exothermic would be energy going out. Cool. And we said that if you're plugging in Q is equal to MC sub P delta T, where Q is the change in thermal energy of the system, okay, we said that actually your final temperature of your system is going to be less than your initial temperature, okay? So then you're gonna get a negative Q. So here, Q is actually negative. Q is negative, it's less than 0 for exothermic processes. Okay, so here, the system is giving off its energy. So the system actually is getting colder, and outside the system is getting warmer. So here's these props. This one, I'm gonna have you guys share. I don't know if these will work. This one, I don't know if that will work. So the way these work is this is a saturated solution, yeah. It's a saturated aqueous solution of just a salt called sodium acetate. And so what you do is inside there, and I don't know, maybe just one of yours, but you see like that thing that looks like a dime. So yours probably won't do this, but for y'all that's still liquid, take that dime and kind of bend it. Yeah. And what you're doing when you bend it is you're disturbing. Oh my God. So look at this. So look at hers is just now. Oh my gosh. Oh my gosh, that's so cool. Isn't that neat? I'm so surprised. Yeah. It's okay, you can hold it.
It's super hot.
It is. Exothermic. So the system is losing energy, but it's giving thermal energy off to the outside of the system, which is your hands or whatever.
Where's the
Amazon. I guess. Amazon.
So they only work once.
What's that?
They only work once.
No. So what I'll have them ready to go so you can do it tomorrow. So all I gotta do, it comes with instructions, is I have to redissolve the sodium acetate. And if you had a sugar solution and you wanted to get it dissolved, what would you do? Like it was sludgy.
What?
Like if you had sugar water and you're like, hey dude, I want all sugar to go in my solution. There's a way to make that happen.
Just evaporate it.
Not evaporate it, heat it up.
Okay, right.
Heat it up and at different temperatures it'll dissolve again. So what I'll do before y'all come to the lab tomorrow is I will boil those in water and then redissolve the sodium acetate. But now the trick with the little pouches you had is that sodium acetate that is it's a super saturated solution. So super means it's just kind of tenuous, it's kind of on the edge there.
I really want one of these. Is it like expensive?
No. And then you just like, boil it and it'll come back. My husband got him because he's like, at the time, I don't do it right now anymore, but with my telescope, I would be out there and it's like -10 and such, taking pictures because, yeah. And he's like, you should have these. So anyway, he got me.
How long do these last? Like,
Yeah.
do you know?
Well, it's already, you'll know, like, probably before the end of the period, it's going to be kind of cooled down. So it won't keep giving heat. It's just the initial, aren't those fun?
Yeah.
I will send out a link.
Can we hang on these for the rest of the period?
Yes, you can hang on. That's very good.
So is this similar to the heat packs you get used at stores?
Yeah, the heat packs at stores, yes, you shake them. And so this is, let's see, this isn't a chemical process. This is just a physical process where that sodium acetate that was suspended is coming out, precipitating as exothermic. The things that you get, like the little, because I have this too, they need air because I think it's iron. Like there's iron in the packet, and it's actually a chemical reaction with air. It's also exothermic, the chemical reaction is. So those aren't reusable, but these are. I don't think you put in the microwave because it's got that metal thing in there. But very good, exothermic. So if we can't tell, something that's gassy doesn't mean it's exothermic. I would imagine, if you put your infrared here, it would be hot. So this is, of course, the surroundings, and the beaker is the system. Okay, so that would be exothermic. We could kind of show it this way, where the system is giving off energy. Okay. Now, actually, we're going to talk about the energy of the system, and it's not very, I got to thinking when I was getting ready for this lecture, it's not very obvious, but the system, as it gives off energy, actually it loses energy. So we're going to actually talk about the internal energy of the system. So, if you burn, anything that burns combusts. Of course, we talked about burning hydrocarbons, and you take the carbon and hydrogen, react with oxygen, you get carbon dioxide and water, and a lot of heat, exothermic. So this right here, well, I'll say what all these variables mean. First off, we know what Q means. So we have another equation. What's this look? For Chem 2, this is Gen Chem 1. For Gen Chem 2, when I have equations, I will give you like an equation sheet. I don't give you equation sheets because you don't have enough equations yet. So you're just going to want to kind of get this under your belt. But Q, we said, is this same Q. Q is equal to mc sub p delta T. It's the change in thermal energy of the system. Well, I'm going to add to this term. Work, W, that big W is the work term. And that is work either done on or by the system. So I'm looking for my little thing. Just to kind of clean that up. It blends in. Like have that little silver. Oh man, okay. This might work. Oops. No, it won't. So anyway, what I was gonna do is W, I was gonna amend it and say W is work done on or by the system. And we'll kind of see what does that look like. Okay, Q is change in thermal energy of the system. W is the work done on or by the system. And then anytime you see the triangle, that means change in. Triangle is the Greek letter delta. So we say delta U. Okay, and where delta U is the change in energy of the system. Makes sense. Basically, we say there's two things the system can do. They can heat up or cool down, or can do work or have work done on it. That's it. That's all that means. So let's see what this looks like. We said if Q is positive, that must be endothermic, right? Okay, so that means energy or thermal energy given to the system. Well, the whole W term, I said it could be work done on the system, in which case it's positive, but if the system does work, it's negative. If the system performs work basically on its surroundings, then the W term is negative. So sorry, I might have said that wrong, but if work is done on the system, it's positive. If the system does work, then it's negative. But here we go. What if you take a positive number plus a positive number? What's your number going to be? Positive, exactly. So the only two scenarios that we get here with endothermic, energy put into the system, and work done on the system, is a positive delta U. It makes sense, doesn't it? Now, we have a few other scenarios, though, as you might imagine. So here we go. Here's a kind of breaking down into parts. to summarize, and remember I told you that you're going to want to somehow get under your belt or in your mind or in your heart, this whole symbol of the positive Q means endothermic. Energy's put in. Okay. Negative Q means exothermic. The system is giving off energy. Here we go. We just talked about a positive work. It means that work is done from the surroundings onto the system. Makes sense. And then the overall energy of the system, which is delta U, would be positive. Well, here we go. Here's a negative W. In that case, the system is losing energy in the form of work. The system is doing work on the surroundings. So those are your kind of four possibilities that go together. Okay. So I hope I can find my pen. So here's a figure from OpenStax that you can, if you look at the top part, it has the possibilities where, let's see, Q is negative, exothermic, and W is negative. Does that make sense? Like up here, you take this, split the green egg-looking thing at the top. You have Q is negative, exothermic. You have W is negative, in that the system is doing work on the surroundings. So what's your U going to be, your delta U? I mean, positive or negative? If they're both negative and you add them together, yeah, gotta be negative. Okay, that means it's losing internal energy. And this was the scenario we talked about before. This would be endothermic, Q, thermal energy put in. This is work done by the surroundings into or onto the system. Positive plus positive, that's going to give you a positive delta U. All right. So I'm going to kind of, I just left all my stuff. We had a test today and they had to say, kind of tell us what that was. Anyway. All right, so enthalpy, not to be confused with clear down the road. I think it's in Gen Chem 2, we talk about entropy. You've probably heard of entropy, you may not have heard of enthalpy before. They're kind of distantly related. But enthalpy is actually tracking this energy we've been talking about. Enthalpy is tracking energy. The symbol for enthalpy is an H. Okay. So enthalpy is the tracking of energy, specifically could be thermal energy that is either taken in during an endothermic process by the system or given off during exothermic process by the system. Enthalpy. So remember I said anytime you see the triangle, that's the Greek letter delta. So here we are, we talk about delta H, change in entropy. That's more enthalpy, excuse me, change in enthalpy. That's more what we are going to be doing. It's hard to kind of get a snapshot of the enthalpy at the time, but it's easier to track the change in enthalpy. So we said Q is the change in thermal energy, not enthalpy, thermal energy. But like this says, if you're not monkeying with the pressure, if it's a constant pressure process, which in the lab we don't do much with vacuums and we don't do much with high pressures. So your beaker's usually open to the atmosphere, it is constant pressure. Then any sort of thermal energy change we see in our system is equal to the change in enthalpy of the system. So change in enthalpy is equal to change in thermal energy for the experiments that we'll be working with. So later, maybe Friday, we'll get to this sort of problem. Remember I said when we do the delta Fs, where'd it go? Yeah. Whenever we do a delta T's, whenever we do a delta, it's always final minus initial. So actually we can calculate, and we will do problems like this, the change in enthalpy by taking the final enthalpy and from that subtracting the initial enthalpy. So it's the same sort of delta means change in, and it's always the final state minus the initial state, just like temperature. So this is a great vocabulary word to put on the first part of your Unit 3 exam. I don't know if we'll be there or not, but it's a player in in this topic of, broadly speaking, thermodynamics. Enthalpy is one of many state functions. So a state function is really fun. A state function is what we say independent of the path. A state function depends only upon the final and initial state. I don't care what you did to get there, but it's the initial and final state. I'm going to show an example here with regard to altitude, but to me, a good example is like your bank account. So, the beginning of the month, the end of the month. It's like, so let's say that you started with $300 and you ended with $600. Well, that's great. But in between, what happened? Well, you won the lottery, and got like $100,000. You spent $200,000, so you were $100,000 in the hole, and then you went ahead and borrowed some money and you infused it back up to $600. So that path doesn't matter where you started and where you ended. Okay? It's independent of path. Actually, I think your bank account would care about that. So state function doesn't depend upon path, okay? But so the opposite of state function would be one that does depend upon path. We could call it path function. So elevation is an example of your change in elevation, I guess I should say. Your change in elevation is an example of I don't care what you did to get there. So here we have two options here. We're going to climb from the base to the top of this volcano. Okay? So your change in elevation, it's the final minus the initial. But notice we have two different paths to get there. But your delta altitude, your change in altitude will be the same either way. So if delta H, the change in enthalpy, is equal to Q, the change in thermal energy, if you're at constant pressures, which we are in the lab, then we could go ahead and substitute instead of Q, we could put in our delta H, change in enthalpy. So now we have a restatement of the change in internal energy of the system is equal to the change in enthalpy of the system plus the work done on the system or by the system. Well, here's one for you. They do this all the time in science. Let's push the envelope and let's say, well, what if you didn't do any work? What if work is 0? Or if this means absolute value, right? What if the absolute value or the magnitude of the work term, do you guys know what this double less than means? Anytime you see this, it means very much less than. So this is saying that the work term is very much less than the enthalpy term. Well, then basically it's the same as going to 0 then. It's insignificant. This is all to say that we could go ahead and boil this down to just deleting the work term. Blow it off. So now here we have the change in internal energy of the system is equal to the change in enthalpy of the system. So now I know what to pass out if I'm just trying to occupy people. And I just have one last thought. Now you have to kind of, how do I say this? I brought dry ice the other day. Did I play with dry ice a little bit here? Okay, good. So what dry ice is it's CO2, solid CO2, and it is what we say subliming. It's going right from a solid to a gas. So that's important to know here. So in that little tablespoon there, they have a solid CO2, and they're going to put it in a Ziploc bag. What's the bag going to do after they zip it up? Expand, yep. And I don't know how clever this is, but here we go. Can you see what work is being done here? It's lifting a book, exactly. Actually, in physics, you can go with how much work was done by how far that book was raised and how much mass that book had, and the force of gravity plan. But that's the work that's done. So it's, I think, a little cheesy. So basically, they're just showing that CO2, as it expanded, that's the system. The Ziploc bag would be the system. It's actually then able to do work on its surroundings. In this case, the book is in the surroundings. So for your homework for this, you just got some kind of, you're wrestling with a delta U is equal to Q plus W sort of thing. And kind of making sure that you get the right sign convention. That's the hardest part of the assignment. Make sure it's positive. So we could go on, but I think we'll take a running start at that. That'd be good to do the part 4 in like a chunk. Okay? So that's all I have today. Thanks for coming!